For this last section of polynomial modeling, we're going to look at some more challenging examples where we mix in some of these ideas. So in number 8, we have a rectangular corral that we've seen before, and this one has a specified area. So the rectangular corral of 32 square yards is fenced off and divided into two sections by a stone fence that is perpendicular to two sides of the outer fence. Well, let's try to make a picture that would make sense of what's going on. So I'm going to create a rectangle, and it is divided into two sections. So I'm going to make this division of two sections. And I'm just going to specify this is the stone fence in this case. The outer fence costs $10 per yard, while the stone fence costs $20 per yard. So there's a reason why we want to specify that that is the stone fence, but we don't really know what the dimensions of this rectangle are. This distance up at the top could be x, which would mean the bottom distance is also x, though we don't know how tall this rectangular is, so I'm going to make that a y, which means the other side is also y. While we don't know what the perimeter adds up to be, we do know what the area is. The area is 32 square yards. And to find the area, we do x times y because it is a rectangle. So the area of this rectangle is length times width, or x times y here. That gives me some information. So I know that if we plugged in the 32 there, that x times y is equal to 32. We want to determine the cost of fencing for this corral. So when I think about the outer fence, the cost would be equal to $10 per yard for this x plus $10 a yard for this x plus $10 a yard for the y and the other y, plus the stone fence, which costs $20 per yard. Now that stone fence is also a distance of x, so I'm going to add 20x here. This currently gives me a cost that would be 10 plus 10 plus 20, so 40x plus 20y. Though we want to create a function that only has one input value, and we're going to let the input be x. So I want to somehow replace this y with an expression in terms of x. Because we knew something about the area, I have a relationship between x and y that we can use. So I want to take this and solve for y to say that y is equal to 32 divided by x. That allows me to substitute something in place of y. So if y is 32 over x, then I can put that in this y spot. So I now have a function that says c equals 40x plus 20 times 32 divided by x. We can multiply 20 times 32 over x and get a function that says 40x plus 640 over x. And that's one function in terms of x. So it's a function for c in terms of x. This function has a domain, and so when we think about the domain of this function, we have a rational component that x can't be 0, which makes sense because this x can't be 0 anyway, and a linear component here. And so really there is only one limitation to x, that it has to be at least some value bigger than 0. We wouldn't be able to have a negative x because then you wouldn't have a side here. So as long as x is some positive number, we can find a y that works with this. So then determine C of 8. C of 8 is just going to plug in 8 for our input x. So 40 times 8 plus 640 over 8. And you can plug that directly into your calculator. And we get 400. And if we interpret what that means, x is the length of the stone fence. So when the stone fence is 8 yards long, the cost of the corral will be $400. And there's one more challenge problem at the end, and this one deals with some volume and some, excuse me, not volume, deals with some surface area. So we have a box with a square base and no top that's to be built within a budget of $12. The base costs $2 a square foot, while the walls cost $1.50 a square foot. So let's get an idea of what this looks like. We're going to draw a box. It doesn't have to be perfect. But one thing we know is that it has a square base. So let the side length of the box's base be x, which means that's x and so is this x. The height can be modeled by h. If we look at the budget, that budget is to make the whole box, so make the outer sides of the box. There is no top to it, so there is a base of this box plus 4 sides. All the sides are the same because it is a square base. So if we look at the budget, making that $12 budget, I have $12 to use to make the base, which is an x by x base. That's $2 a square foot. So it's $2 per square foot, which is going to be x times x. So the area of that base is x squared. Plus, we have $1.50 for each of the sides. So $1.50 per square foot of sides. The side here is x times h, and there are 4 of them. So it's going to be 4xh. If we use that to simplify, we would have 12 equals 2x squared plus $1.50 times 4, which ends up being 6xh. This equation can be used to write h in terms of x. So we want to solve for h. That would mean I move this 2x squared over, so let's subtract it. And then we can divide by 6x. That could be reduced, so if I take that and reduce by a factor of 2, everything is divisible by 2. We get 6 minus x squared over 3x. And that now expresses h in terms of x, but we want to then create a volume function. So we're going to use the volume of that box, which is length times width times height. If the volume is length x times width x times the height h, but now we know what h is. It's 6 minus x squared over 3x. We can also simplify that down. All right, this would turn into x squared times 6 minus x squared over 3x. X squared over x would reduce to just x over 1. So that would simplify to x times 6 minus x squared over 3. And I can make that a little bit cleaner by distributing and getting 6x minus x cubed divided by 3. If you want to write that in a standard form equation, 6x divided by 3 would be 2x minus 1x cubed divided by 3 would be 1/3 x cubed. So there's a volume function for that polynomial that has a domain. We would need to write this in factored form to get this domain. And this is not one that's going to factor nicely. So as we look at this, I'm going to take volume is equal to x times, I'm pulling that x out to factor out, and make 2 minus 1/3 x squared. That's still not pretty, but it is at least a factorization where I know x equals 0, and then 2 minus 1/3 x squared could equal 0 as well. We just have to do some algebra to solve that out. So I'd subtract 2 to the other side, and then divide by negative 1/3. You could also multiply both sides by negative 3 and get 6, and that would still give you the same thing. So x squared is equal to 6, which means x is equal to plus or minus the square root of 6. It is often easy to find the domain when we have the factored form because we could look at the zeros. This tells me there is a 0 at 0. There's 1 at negative square root of 6 and 1 at positive square root of 6. Because we know the factored form that gave me the zeros, we can also look at standard form to get an idea of what the end behavior is. It's a cubic function with a negative coefficient. That x cubed has a negative 1/3 coefficient. That means we're going to go up on the left and down on the right. So if we graph that polynomial, we can get an idea of what the volume looks like based off of different x's. Now realistically, the volume can't exist over here because your x is negative. So that function does not really exist on this side. So we limit it to when x is positive because we have to have a positive side length. So x could be greater than 0, but it can't go past the square root of 6 because then the volume becomes negative. That's happening because we end up with a negative height. So for this, the domain of our function v would be equal to 0 to the square root of 6. Now I'm going to use parentheses here instead of brackets because if x is equal to 0, if we include 0, then I have a box with no side and it doesn't have a volume then. The volume's equal to 0. So we don't really have a box if we include 0 or square root of 6. We can use a graphing utility to find the maximum volume. Now in calculus, you'll take a derivative to then find this. But for us, we can plug this into Desmos and find out where is that one particular value. So if I take this function and plug it into Desmos, I'm going to end up with a function that looks like this one that we sketched, and I can find the maximum. That maximum has a point at 1.4 and 1.89, so 1.9. So the maximum volume would be the 1.9 because that's the output, that's the volume that we're measuring in this. Would be 1.9, and this is in feet. All of the dimensions were in feet, so this would be cubic feet in that case.